happening in recent years is we are seeing these applications in which time plays a very important role. We are seeing applications where we are controlling the physical world, we are sensing the physical world, and that requires that the computation's notion of time and the physical world's notion of time be aligned. Unfortunately, at the same time, many technologies that we rely on are making it harder to have precise timing. So the goal of Roseline is to really help applications cope with the uncertainty in timing that is occurring in these computing systems, so that we can have good, robust, reliable, time-aware applications on computing platforms where these kind of uncertainties make it harder to achieve that.
We propose a new way of thinking for time management by introducing a new timing abstraction in an operating system, which we call a timeline. Timeline is a virtual reference time base with respect to an epoch. Multiple nodes can bind to a single timeline, and the timeline not only manages their time sources but also coordinates their tasks according to their desired requirement. There are two key attributes of a timeline: accuracy and resolution. The first attribute, resolution, is the minimum tick requirement of a node with respect to a timeline. This attribute enables the timeline to pick a clock source that best fulfills its resolution or tick requirement. Our Roseline team has developed a Cronus board that provides different clock sources to choose from based on the resolution requirement of a timeline. The second key attribute of a timeline is its accuracy. And the accuracy of a timeline is an asymmetric interval around the true time that determines the maximum error a node can tolerate in its time estimate from all the other nodes bound to the same timeline. For example, if Mike and Hotel nodes want to coordinate their task to the order of millisecond, they both will bind to a timeline with an accuracy of millisecond. And if Mike and Lima wants to coordinate their task to the order of a second, they both will bind to a timeline with an accuracy of second, thus giving an opportunity to a single node, which is Mike in this case, to support two different timelines with totally different timing requirements. This is in contrast to the traditional time synchronization protocol, where a single time reference is provided irrespective of the dynamic application requirements in a network. Unlike this traditional approach, timelines enable vectored coordination, where the nodes synchronize to only those nodes in the network that require some level of coordination, and in this way we can utilize the network and hardware resources efficiently. Finally, for providing applications with simplified time management interface, we have provided APIs centered around our timeline abstraction and a complete architecture that goes along with it. We have implemented our timeline-based architecture and stack in Linux, and in our implementation stack, we did not change the existing timekeeping and timer functionality in Linux. Instead, we provide a parallel system to support timelines for applications. Our testbed is comprised of BeagleBone Blacks, which run Linux operating system, and they're used in many CPS and IoT applications. The source code for our timeline-based architecture and stack can be found in this link.
So there are so many applications, so many exciting applications now that fundamentally depend upon a robust understanding of time. Just to take an example, drones or swarms of drones, the coordination among them depends upon time. The control of an individual drone depends upon time. So ways by which very resource constrained, potentially very tiny devices can have a good quality of time, not just individually but across an entire network.
Time accuracy can have large impact on position estimation. Therefore, we introduce slats, simultaneous localization, and time synchronization. Slats depend on graph realization solution and extended Kalman filter to provide time synchronization and accurate position estimation.
In order to evaluate slats, we developed a custom ultra-wideband test bed based on Decca wave radio. This test bed used Cortex M4 processor and powered over Ethernet, and we developed battery-powered Classify. We used ROS for visualization and control.